Hello, my name is Leslie Smith, and today I will be analyzing the hydroxylysine molecule by using the topics I learned in my Organic Chemistry 1 class. To begin with, hydroxylysine is an amino acid that is derived from lysine, which is found primarily in collagen, providing stability, toughness, and resiliency of connective tissues. The molecular formula for hydroxylysine is C6H14N2O3. Both the melting point and boiling point vary depending on the form and purity of the compound. The melting point is 215 to 225 degrees Celsius, and the boiling point is 416 plus or minus 45 degrees Celsius. This molecule is soluble in water. Moving forward to the hybridization of hydroxylysine. The hybridization is as follows. The green dots represent sp3 carbons with a bond angle of 109.5 and a tetrahedral shape. The blue dot represents an sp2 carbon with a bond angle of 120 and a trigonal planar shape. The pink oxygen is sp2 with two lone pairs, making the bond angle 180 and linear. The red oxygen is sp3 with two lone pairs, having a bond angle of 105 and a bent shape. Finally, both the orange amine groups are sp3 with one lone pair, having a bond angle of 107 and a trigonal pyramidal molecular shape. The functional groups for hydroxylysine are carboxylic acid, alcohol, or also known as hydroxyl, and amines. For the resonance of this molecule, the only movement of electrons that can occur are in the carboxylic group. As shown, the double bond O breaks a bond and receives the electron pairs from the bond. By breaking that bond, a pair of electrons from the O bonded to the H creates a double bond. This movement of electrons is due to the principle that states if you break a bond, you must make a bond. This leaves the O with a negative charge, and the O in the OH bond receives a positive charge. The reason in which the lone pairs in the alcohol group and the amine groups cannot move and create more resonance is because it will break the octet rules for the carbons in the parent chain. After resonance takes place, a resonance hybrid can be created by combining the structures. This slide demonstrates the partial charge in the molecule due to the combination of movement and resonance. In the carboxylic group, the O is partially negative and the OH is partially positive. The blue dashed line demonstrates the movement of electrons due to breaking a bond and forming a new one. Now let's talk about the acidity and pKa of this molecule. It is noted that the alpha amino group is the one near the carboxyl group, as it is a functional group that is attached to the alpha carbon on the chain. The other amine group and the alcohol group are considered part of the side chain. The pKa for the side chain amine group is approximately 10.5. The alcohol pKa is approximately 16 to 18, indicating that this group is a weak acid that is still able to participate in hydrogen bonding. The pKa of the alpha amino group is approximately 9.67. Finally, the pKa for the carboxylic acid is roughly 2 to 2.5, since the alcohol group influences that group to become a bit more acidic. Overall, hydroxylysine is a basic amino acid that is positively charged. To name this molecule, the first step is to find the parent chain, which is the longest carbon chain. In this case, it contains 6 carbons, which are shown above in red with the correct numbering sequence. We start numbering from the carboxylic group due to that carbon having more substituents attached to it, giving it numbering priority. There are 2 chiral centers which give us our beginning S in our configurations. From there, we label our groups, add prefixes, and stereochemistry labels, which results in the IUPAC name of this molecule to be 2S, 5R, 2, 6 diamino 5 hydroxyhexanoic acid. Each part of the molecule is highlighted in accordance to how the name of the molecule was created. As previously mentioned, there are 2 chiral centers in this molecule. The chiral carbons marked in red show that the sp3 carbon is bonded to 4 different groups. We begin by assigning priorities in each stereogenic center based on atomic weight. For the chiral center on the left, the priorities are labeled. This configuration turns counterclockwise. However, the lowest priority atom, which is the hydrogen atom, is on the wedge, which causes the configuration to swap. The S configuration becomes R. For the stereogenic center on the right, the priorities are also labeled. This configuration also turns counterclockwise, and since the lowest priority atom, which is once again hydrogen, is on the dash, the configuration remains as an S. Enantiomers. The enantiomers for hydroxylysine are pictured on this slide. Both the top and bottom pictures on the left side are the original molecules. Enantiomers are non-superimposable mirror images of each other that can be swapped by creating two groups on the molecule to swap. As shown, the dash and wedge atoms were swapped, creating enantiomers. In this slide, the Fischer projection of hydroxylysine is drawn. To create this projection, the highest oxidized carbon is located at the top, which belongs to the carboxylic group. The horizontal lines represent the bonds coming out of the page, or in this case, the slide, and the vertical lines represent the bonds going into the slide. Each intersection between the skeleton of the projection represents a carbon atom, of which there are 6 in hydroxylysine. For the stereogenic centers, placing the highest priority atom is tested by understanding the configurations of the chiral carbons. Since the second carbon is an S configuration, the NH2 must be placed on the left side, which makes the H atom a wedge, causing a swap from R to S. Similarly, the fifth carbon is an R configuration, meaning the OH needs to also be placed on the left side, making the H atom a wedge, causing a swap from S to R configuration. Moving forward to the nucleophilic and electrophilic sites of hydroxylysine. A nucleophile is an electric-rich species that donates an electron pair to form a bond. This molecule acts as a nucleophile where the primary nucleophilic site is the amine group on the side chain. This amine group is on carbon 5. The lone pairs on the nitrogen make this functional group highly nucleophilic as it is electron-rich. Additionally, the alcohol group can also be considered a nucleophile, even if it is less reactive. The oxygen atom in this group can behave as a nucleophile due to its lone pairs of electrons. However, the amines are more nucleophilic than the alcohol due to its chemical environment and physiological conditions. Contrary, an electrophile is electron deficient, accepting an electron pair to form a new covalent bond. Hydroxylysine does not possess electrophilic sites, though in advanced biology, lysine residue can be chemically converted to contain very weak electrophilic sites, such as a carbon adjacent to the carboxyl group and the carbon atom bound into the alcohol group, but that is not the dominant role for this amino acid. The IR spectrum for hydroxylysine is expected to contain an OH stretch that is very broad if the carboxylic acid is protonated. The side chain alcohol contains a narrower stretch. These peaks appear in the 3200 to 3600 region. For the amine groups, the primary amine stretches from 3300 to 3500 region, which often appears as two weak medium peaks. The NH bending appears in the 1550 to 1650 region. The carboxylic acid stretches from 1700 to 1725. The side chain alcohol shows a peak in the 1000 to 1260 area. The CN stretch is expected to be approximately in the 1020 to 1250 region. Finally, the CH2 bendings are expected in the 1450 to 1470 area. Carbocation structure and stability. This slide explains why carbocation stability is an important concept when discussing hydroxylysine, even though this molecule does not contain an alkene. Electrophilic addition reactions often proceed through carbocation intermediates, and the stability of these intermediates determines where and how reactions occur. Since tertiary carbocations are more stable than secondary or primary, this helps explain how the electrophilic processes happen in organic reactions. Hydroxylysine is formed biologically through enzyme control hydroxylation of lysine, laying the foundation on how substituents stabilize which develop a positive charge. So by connecting molecules like hydroxylysine with the carbonic ion principles, it explains why certain functional groups form what they do and why enzymes direct certain reactions. As previously mentioned, this molecule does not have a carbon-carbon double bond, but the conversion of lysine to hydroxylysine is a hydroxylation reaction which is similar to alkene hydroxylation reactions. Enzymes such as lysohydroxylase perform a selective oxidation to add an OH group, which forms hydroxylysine. This reaction mirrors alkene hydroxylation through oxidation, forming a new CO bond and stereochemical control. This slide shows my references, and that is the end of my PowerPoint. Thank you for your attention.